introduce Jasper Rinalda today. So he's a visiting Fulbright scholar, so he's here working in the College of Health Sciences. So he's come across from Roosing Research and Development over in the Netherlands, and also works at the University of Twente. So he began, began like he did his undergraduate over in the Netherlands as well at VU University. And he did a thesis looking at the effect of adding weight to limbs and looking at most economical step length. I'm saying that because I know some of you are interested in that. All right, so here's a great resource for you. He then went on to do a PhD in biomedical engineering at the University of Twente, where he focused on looking at preventing pressure ulcers in spinal cord injury. And then his postdoc returned him back to an interest in running mechanics again, where he's looked at the effect of shoe concepts at running mechanics. He's also got some pretty impressive out-of-work accomplishments as well. So browsing through your CV, I noticed that you're a 12-man Ironman triathlon finisher, including running at the World Championships twice.
Okay, thank you, Mike. Thanks for the kind introduction, and welcome to all here at the Friday morning after the game yesterday evening. So I'm glad you all show up. There was a lot of running yesterday evening on the field, but I focused my talk on running outside or just running. And I will talk you through a 3D analysis of running technique, running mechanics. I mean inertial magnetic measurement units. And for those of you who are familiar with that, I hope that after the presentation you know what they are and what you can do with them. So, just to get back, this is Forrest Gump running, actually for Alabama, but a different team, so I thought I'd be safe to use this one in the presentation. But the running is, well, as you all know, very popular. In 2009, about 70 million people worldwide ran, and it is assumed that the number has increased since, and it's still increasing. If you look at the popularity of running races, at least in the Netherlands, but what I see here as well, that figure is about to increase even more. However, a lot of those runners get injured, and injury rate is varying a lot. It depends on the literature that you take a look at, but it's somewhere between 20 and 80%, depending on the subject population. And the re-injury rate, so runners that are injured and recover but then get injured again, is also pretty high. And you can question if there is some relation with running technique. Well, Forrest had a very specific running technique. He didn't get injured, but you can question if there's a relation with running technique. So to investigate running technique, you need some kind of motion analysis. You need to quantify technique in specific measures in order to find relations between running technique and eventual injury development. Ebert Muybridge was one of the pioneers of motion analysis, and he started with analyzing animals. And basically he just took pictures, photographs of them, and put them sequentially, and then you get moving pictures. And I thought, well, the horses are very specific for this region, and buffaloes are all American as well. But that also he did focus on running as well. So he made 2D analysis of running mechanics, running technique. Basically, it's difficult to calculate any angles from this. The pictures weren't very sharp, and for some reason at that time there was a lot of nudity in the pictures as well. I don't know why that is. Luckily, that has changed. So that was an introduction to motion analysis, how it started a long time ago. It has evolved ever since, and nowadays motion analysis is applied on a lot of different fields. In athletics, it is used often, but then it's more of time like this. So you have a runner first. Again, he started fresh from his house in Greenbow. He has a good technique. Well, we're not sure because it's a 2D picture, but it looks nice. And if you compare it with a world-class athlete, how we are supposed to run, well, there are some similarities. So Forrest is doing okay. And even if he got fatigued, well, this is from a different angle. good, okay. Um, I'm a bit joking, but this is how motion analysis in athletics most of the time looks like. You have a 2D image, a picture, you have some kind of optimum, a world-class athlete of who you think his running technique is okay because it's running fast, you try to, well, match that with your runner. But is there a relation between running technique and injuries? If you look at the literature, there is hardly any evidence for a specific relation between kinetic or kinematic abnormalities in running technique and injury development. And it can be as a consequence of that most studies are retrospective in nature, where the runner is already injured. And you have the chicken egg problem. You don't know if the abnormalities that you're witnessing are a consequence of the injury or that they are actually causing the injury. Prospective studies might be a solution, but there are hardly any prospective studies out there. The few that are from UK, and for instance, relation between excessive hip abduction and patellofemoral pain syndrome has been found. But prospective studies are rare, and basically we don't know much about the relation between running technique and injury. And it can be a consequence of the fact that there's not one optimal running technique, but there's an optimal individual running technique. So not everyone needs to be running like Usain Bolt or like a top marathoner, but every runner has a specific running technique. And Ben O'Nick now from Canada defined a preferred movement path. That's some kind of emotional path that a runner tries to execute as much or as long as possible. It's not only for running, but it can be translated to every movement that you're making, a preferred movement path. It's dictated by anatomy, so how are we built, and by motor program, and it's probably or presumed to be guided by efficiency, optimizing efficiency, and minimizing impact or getting impact within known limits of the body. And as a consequence of training, anatomy, anthropometry, and physiology, so how is your body built? If you're more muscular, it's probably a different running technique. You have probably a different running technique than if you have less muscular. And like for stride length, stride frequency, well, my view is that a lot of you are interested in that. We hope to have published this paper on this in a couple of months. It's in the last stage of the review, and one of the results is that the weight distribution of the individual runner's leg is a good predictor of your optimal stride length, stride frequency. So how are your muscles located in your leg? What is their origo, insertion, those kind of things. They dictate an optimal running technique. A previous injury might also cause a optimal movement path. So what are the factors that contribute to the choice for a particular running technique? The amount of mechanical work. If you're running slowly, you require a different technique than if you're running a 5K on a track. So the amount of mechanical work. Also, if you're running uphill or downhill, it's pretty obvious, but it requires a different technique. Muscle efficiency, running economy, differs between runners. Also, it dictates a different technique. Movement variability, training status and previous training. If you're a novice runner or you're a very highly competitive elite runner. And then, again, anatomy, anthropometry, morphology, physiology. So is there an optimal individual running technique to avoid injuries? And if so, if there is an optimal running technique, as long as you stay running in that optimal running technique, you won't get injured. But a lot of people get injured, so how do you get injured if there is an optimal running technique? And fatigue might have some influence on that. This is the envelope of function. This is a model developed by Dye a couple of years ago to see how failure of certain structures in the body can result to injury. So if you have that zone of supraphysiological overload, my apologies for the rather not very readable picture, but that's the middle gray part. That can be your preferred movement pattern. As long as you stay within that movement pattern, you won't overload your structures. You won't get injured. If you're under that supraphysiological overload, you won't get injured, but you won't improve. So that's not a goal of the typical runner. If you're outside, above that middle zone, there's a zone of the structural failure, and there is where you get injured. but how do you drift into that zone of structural failure? Or by increasing your mileage, increasing your speed, but also by fatigue. If you get fatigued, you're not able anymore to keep your movement pattern within that middle zone, and injuries can develop. So fatigue and running technique, we can assume that fatigue influences running technique. It's quite obvious if you look at races, for instance, and visually compare the technique of runners at the beginning and at the end. There are some nice examples in history. This is Dorando Pietri. It's an Italian runner in the Olympic marathon of 1908 in London. And he just started running. He ran for a couple of years, but he was, well, for that time, a pretty fast runner. And the Olympic marathon in London was the third marathon that was run at the Olympics. The first was in Athens, and then it was only 40 kilometers. Next year is also 40 kilometers, and in London they added the 2.195 kilometers because the royal family, the British royal family, wanted to see the finish in front of their palace. So they added another loop, and that's why our marathon, 26.2 miles or 42.195 kilometers, got its current distance. So Pietri had to run another 2 kilometers, and that was probably a bit too much for him. He was leading from the 30-kilometer mark, and in the last 300 meters he was fading, and it took him 10 minutes to complete the last 300 meters. There is no video footage as far as I know from that, but you can see that his running technique at the beginning is different than his running technique at the end. He crossed the line in first, but he was disqualified because of outside assistance, as you can see here. So this is a funny example, but we can assume that fatigue influences running technique, but how exactly does it influence running technique, and are there individual differences? If we assume there's an individual movement pattern, fatigue might have individual differences, cause individual differences as well. So we assume that fatigue influences running technique in an individual way. So what is fatigue? Basically any exercise-induced reduction in the ability of a muscle to generate force or power with either peripheral or central causes. Well, peripheral muscular fatigue or system fatigue, and central fatigue decrease in the muscle force as a result of a decline in motor neural output. So you're not able to activate your muscles good enough anymore. During marathon running, a large inter-individual difference of variability in fatigue has been witnessed. Del Cosa did an interesting study 2 years ago where he took a lot of blood samples to analyze fatigue on hormonal level. He found large inter-individual difference between runners. But basically it doesn't matter that much for a runner. A runner isn't interested if it's peripheral or central fatigue. The end effect, the inability to maintain a certain power output, a certain velocity is what is most interesting to the runner. So the end result is the same. A lot of studies have looked into the relation between fatigue and mechanics, and at the end of the 70s, early 80s, the high-speed video cameras allowed for 2D analysis of running technique on the athletic track. Bates and Elliott did a lot of work on that. Let runners run on the athletic track, fatigue them, and see how their running technique changes. And they found effects of fatigue on stride length, probably because they were running slower as a consequence of fatigue, and on segmental body position, so on kinematics. And they don't specify that into detail, but they suggest that the coach that can identify the changes in running technique as a consequence of fatigue would be able to help that athlete improve and increase the likelihood of success. So there was a first step into investigating the relation between fatigue and mechanics. So after that, laboratory studies increased because of optical motion analysis systems that allow for 3D measurements in a highly standardized and controlled setting. Force plates, instrumented treadmills, and basically standardized measurements of kinetic, kinematics, spatiotemporal parameters were possible while fatiguing a runner in a controlled setting. So you could manipulate all kinds of variables to see how it affects running technique. However, if you look at the results from all those studies, well, not all those studies, there are a lot more. If you look at kinetics, there are differential effects on kinetics. So fatigue changes kinetics, that's for sure. But for instance, tibial and sacral impact accelerations increased while shock absorption decreases. Other studies found fatigue lag impact to increase while shock attenuation increases. So that's the opposite. Localized muscular fatigue influences loading rates. There was an increase as well as a decrease in loading rates, depending on the study you look at. Impact decreases as a result of fatigue, and shock continuation decreased while impact did not change. So a lot of differential effect. Is not easy to draw one specific conclusion from these studies and the relation between fatigue and kinetics. Kinematics, basically the same picture. Morgan found no kinematic effects of fatigue after 20-minute run in trained runners, so that indicates that they run exactly the same off in the fatigue state as they did in the unfatigue state. Others found knee flexion and foot strike decreases, or it increased in other studies. So peak knee flexion has something to do with shock absorption capacity, increases as well as decreases as a consequence of fatigue. Others found small alteration, lower extremity kinematics, no changes in joint timing, where it took decrease in peak knee flexion velocity. So a lot of differential effects of fatigue on kinematics. No interaction effect between fatigue and limb dominance was found in kinematics. That's something you can assume that if you have a dominant leg, it's probably stronger than one fatigue, as much as the other leg. That wasn't found as well. Gender effects, well, there were gender difference in the effects of kinematics, angle, knee range of motion. Basically, it's also difficult to draw a specific conclusion from the relation between fatigue and kinematics. For movement variability, basically the same holds true. So what can we conclude from the lab studies that have investigated fatigue? So fatigue a runner, see how it changes kinetics and kinematics. Differential effects on kinetics and kinematics. Basically the only thing that was consistent was a reduction in stride length. That's probably a consequence of a reduction in velocity as a consequence of fatigue. So if you run slower, your stride length decreases probably. There was a large inter-individual variability. Most of the studies report a large inter-individual variability, so they look and they analyze the data on group level, but indicate there is a large inter-individual variability. But those individual values are hardly presented. It can be that the type of induced fatigue differs between the studies. So I just said that it doesn't matter for the runner if he's centrally or peripherally fatigued, but some of the studies, due to the highly standardized setting, just locally, or peripherally, or centrally fatigued the runner. There were studies that let the runner run for 24 hours on the treadmill. That induces a completely different kind of fatigue than if you're fatigued fairly rigorously in a couple of minutes. And Mercer already in 2003 stated that it's probably the complexity of fatigue and the participants' experience of running while fatigued. So how well are you able to handle the fatiguing situation that accounted for the difference in results between the studies. So it's difficult to conclude anything specific from those studies. So those were all done in a lab situation, and it might be that the lab situation, although it's highly standardized and highly controlled, is very specific for the runner who's running outside. I suspect that not all of you are always running inside a lab, and probably most of the time running outside, where you have the environmental differences, be going uphill or downhill, curbs that you have to avoid, different surfaces if you're running on trails or you're running on concrete. So there's a lot of differences between running in the lab or running outside. So the measurements in the lab setting on a walkway or an instrumented treadmill are highly standardized, but they have limitations. They're very cyclic, repetitive, and the movement variability is very low. And they're pretty age-specific. So measurements in a sport-specific setting, in the field or on the road, with high-speed video analysis, like they started with in the 70s, or the application of inertial measurement units might shed some new light on the topic. So, concluding, lab-based studies, differential effects of fatigue on running mechanics, kinetics, kinematics, spatiotemporal parameters, and movement variability, large inter-individual variability, but those values are presented. And the type of induced fatigue differs between the studies. So if we look at fatigue in sports-specific setting, there's also some work done in that area. Larson, for instance, analyzed foot strike patterns of runners during an actual marathon. So he placed cameras at the 10 and 32K marker and analyzed all runners that crossed that point, and video analyzed their foot strike pattern. But what he noticed was that there was an increased frequency of rear foot striking as a consequence of probably as a consequence of fatigue. At least more people were rear foot striking at the 32-kilometer mark than that they were doing at the 10K mark. The frequency of rear foot strikes at 10K was already pretty high, in contrary to what is common assumed. Chen Rover did a similar study looking at kinematic changes as a consequence of fatigue. They also placed cameras, this time at 8 and 40-kilometer mark. So they did a 2D analysis of kinematics. But what they saw that was running speed decreased and stride length decreased. Well, that's something that's linked. They also found knee flexion at foot strike and during swing decrease. So knee flexion decreases at initial contact, so at early stance, and during swing. During swing is probably a result of that decrease in velocity, and a reduction in knee flexion is probably a consequence of a limited shock absorption. So this is a picture from their article. At the race course, they have 2 cameras capturing a space of 5 meters. They had a lot of problems with, I don't know which marathon they measured, but it was a pretty big marathon with a lot of competitors. So they had to, they had a different data set at kilometer 8 and they had at kilometer 40, so they had to match all runners. It was a difficult situation. And what was interesting is that they also related their results to the, or made them velocity dependent. So the first conclusion was that running speed decreased and that stride length decreased, but if you relate that to the decrease in running velocity, actually there was an increase in stride length. So although they were running slower, normalized, their stride length increased. And same all true for contact time increase as well, knee flexion decrease, and hip extend well. So a lot of interesting results from that study, but it's still 2D kinematics. This was a first step in bringing basically the lab to an athlete, so bringing the camera to the course and measuring them in their real-world setting. Probably a marathon is not very specific for every runner, but it's a more real-world setting than a lab. So bring the lab to the athletes, and therefore we need ambulatory measurements. In this case, not the runner was equipped, but the course was equipped with cameras. The developments in sensor technology allow for a continuous 3D kinematic analysis of movement in sport-specific setting. And that's by means of inertial sensors. Inertial sensors, they have been around for, I think, 20 years now. The simplest ones are the step counters that you get free by a pack of cereals. Those are inertial sensors as well. They count how they are moving, and the frequency of their movement is related to your steps. That's what they assume. But the inertial sensors typically contain an accelerometer, so they measure how they excel, a gyroscope, how they are turning, and a magnetometer. So the easiest of the simplest one is just an accelerometer. The more high-end versions of inertial sensors have a gyroscope and a magnetometer as well. And the first, as far as I know, to use those in the sport-specific setting in relation to fatigue was Legree in 2006, and he measured one inertial sensor where he placed it on the sacrum, and he measured as a consequence of fatigue more movement in the medial over the mediolateral axis. So that's you want to move in the anterior posterior of your anterior posterior axis. So there was a more unwanted movement as a consequence of fatigue. Storman from Zurich in Switzerland measured kinematic changes as a result of fatigue by means of inertial sensors, and they coupled, I think, they used 18 inertial sensors on runners, and they had a very interesting group of novice runners and trained runners. They fatigued them, in the lab situations on a treadmill, and they fatigued them outside the lab, so they could combine those data sets. And they found kinematic changes for all runners, as for all runners changed in the same direction. They found certain parameters that changed for the novice runners, but did not change for the experienced runners. Trunk forward was one of those parameters. And they had parameters that changed for individual runners, so there was no general pattern to be found in that. But they also more or less conclude that there's an individual preferred movement pattern for each specific runner. However, they analyzed every inertial sensor individually, and they weren't able to combine these inertial sensors, these 17 inertial sensors, into a full kinematic analysis, so they weren't able to calculate joint angles, which is something that you want for a complete kinematic analysis. So that was basically our starting point. At our institute, we have been working with inertial sensors for a long time, and we are fortunate to work together with Xsense, which is a company, it's a spin-off company from the university, and a colleague of mine was one of the more or less inventors of the technique, and so we closely collaborate with them, and we have been doing a lot of work on inertial sensors and movement analysis with inertial sensors for a couple of years. After my studies on runners in the lab situation, I thought, well, can we investigate fatigue in the most sport-specific setting? So we want to know that the runner is fatigued without a specific fatiguing protocol, and we want to measure kinematic changes. So we started measuring during a marathon. It was the only reference that we had, the two studies from Larsen and from Chen Rover, kinematic changes during a marathon in sport-specific setting. So we equipped 3 runners with 8 inertial magnetic measurement units during a marathon, and we placed them on the, well, basically lower body, feet, lower leg, upper leg, sacrum, and sternum. So we had all segments that in our view were interesting for a kinematic analysis: feet, lower legs, upper legs, pelvis, and trunk. And those sensors transmitted their data wirelessly to a receiver which was mounted there on the bicycle handlebar. So we had a very small lab setup on our course. So the runner equipped with 8 sensors, continuously transmitting data to a receiver. Problem was, there were more problems. First problem was that the battery life of the individual sensors was 3 hours. So we had to decrease our runners accordingly. Second problem was that the distance between the runner and cyclist could not be more than 10 meters. And in a marathon with a lot of runners and with turns and all the things, it's difficult, so the cyclists had to follow the runner closely and sometimes had to yell at other runners to move out of the way in order to not disturb our experiment. I would advise you to measure during an actual marathon. So we used inertial sensors from Xsense. Those are matchbox size sensors that contain an accelerometer, a gyroscope, and a magnetometer. So they're the high-end inertial measurement units. IMU is the typical abbreviation for those inertial sensors. We use IMMUs, and we have a magnetometer as well that provides additional data from which we can eventually analyze the segment orientation. So basically, these sensors, an individual sensor, if you're moving it, it continuously gives data about how it's moving over 3 axes. So it has a roll, a pitch, and a jaw angle, and it continuously gives information how it is, how those angles vary according to how they are moving. So an individual sensor only knows how it is moving and with what kind of acceleration or with what kind of angle it is moving. It doesn't know where it is, or where a potential other sensor is, or where the segment it is connected to is. So it only gives data, and this is a representation of the sensor with the 3 axes, and it continuously gives information about how it's moving. If you have that information, you basically don't know anything more than how the sensor is moving. So you need a filter to integrate the accelerometer, the gyroscope, and the magnetometer. And luckily for us, Xsense has done a lot of work in developing a Kalman filter, which continuously combines the data from the 3 segments, from the 3 sensors, basically, to orientation of the sensor. So you have 3D accelerometer, you have a 3D gyroscope, you have a 3D magnetometer, you use a Kalman filter, and then you go from the global coordinate system, so how the sensor is moving in space, to a local coordinate system, how the sensor attached to a segment is moving in space. So then you know how the segment is moving in space. So if you place a sensor on the foot, without the Kalman filter, you only know how the sensor is moving, you have no idea where the foot, for instance, is. If you apply the Kalman filter, you know where the foot is moving in space. You still don't know exactly where it is, but you know where the ground is and how it's moving relatively to the ground. Then you know where one segment is, but still the sensors aren't interconnected, so you don't know where the other sensor is. And for the kinematic analysis, you need to know where the other sensors are, so you have to perform a very rigorously static and dynamic calibration. It takes up to about 1 minute, so that is not too much. But you have to build up your biomechanical model from the sensors. So you define movements over all the 3 axes that a sensor can give data about. And if you do that smart, you can build up a 3D kinematic model, just as the ones that derive from the optical 3D motion systems. So then you have basically your 3D kinematic analysis without the lab setting. And you can perform it by just placing those small sensors on the body. You can perform it basically everywhere, as long as there's not too much magnetic disturbances, and as long as the receiver is closely to the subject. Magnetic disturbances are almost everywhere. A lot of concrete is armored with iron inside it. A lot of floor parts are concrete. In a typical lab situation, if you're running on a treadmill, for instance, instrumented treadmills, you have a lot of iron in it. All those things influence this data that you can account for. So this is one of our runners during the marathon. So we were able to integrate those 8 sensors into a running stick figure. This was what happened. We defined 4 stages during the marathon, basically 10, 20, 30, and 40 kilometers, and analyzed kinematics, ankle, knee angle, hip angle, and center of mass oscillation for the 3 runners. This is runner 1, where a lot of changes happen during stance. So those vertical lines are toe off, shifts a bit depending on the stage. This is the beginning, so red is the beginning, purple is the end of the marathon. Most of the changes here during stance, as well as for the knee, a lot of changes at the hip and center of mass. There are some changes, there are more changes for this is right foot on the ground, this is left foot on the ground. So more changes for the left foot and for the right foot. Runner 2, different profiles. For instance, no changes during stance phase for the knee. So nothing changes in knee angle. And less changes, for instance, the hip, but more changes in the center of mass. Also more higher oscillation for center of mass for runner 2. Runner 3, a different profile, lower oscillation, changes at stance phase, for instance, more changes between the beginning of the end and for the end of the bubble. This is more visually represented. This is interesting. You see changes in the kinematics, you see changes in hip, knee, and ankle angle. You don't know if they're a consequence of fatigue or they're just some kind of adaptation strategy. So if you're running slower, which all of the runners did during the marathon, your kinematic changes, especially your knee angle, for instance, during swing changes. This angular acceleration, this is the beginning. This is for 3 stages, so that's a bit different analysis, but this is toe off. So this is the amount of acceleration your ankle or your foot has when after toe off. So we can assume that it has some relation with the ankle power which you push off. At the beginning of the marathon, power is almost twice that at the end of the marathon. So you push off a lot less at the end of the marathon. Center of mass, acceleration, so just showed oscillation. This is acceleration. Basically, it is the impact measured at the center of mass. For the three runners, so this is right foot on the ground, left foot on the ground, and what you see is that impact increases from stage 1 to stage 4. So even though the runner is running slower, impact increases. So even though you're running slower, your stride length decreases, your impact goes up. Normally, if you're running slower or you're running with a shorter stride length, your impact goes down. So this is an indication that the runner is getting fatigued. But still, we don't know that much about it. We see inter-individual changes in joint angles. We see an increase in center of mass oscillation. And we can conclude that fatigue influences running technique, but we don't know how exactly. We see some individual changes. But due to the low internal validity of this study, so we increased a lot in external validity since we're measuring in a sport-specific situation, but a lot of things happen that we can't account for. So our internal validity of the study was rather low. So therefore, we went to the athletic track, did some shorter measurements in a slightly more controlled study. And this was on the outdoor athletic track. In the coming weeks, I will be measuring here at the indoor athletic track. That's even more standardized controlled, so that's a good thing. To perform 20-minute threshold runs, we used with Jack Daniels, a famous athletic coach and researcher, and he developed a threshold run at a critical velocity, which is more or less your 10-kilometer pace, and we let 8 runners run for 20 minutes on athletic track. So they ran laps, and we followed how the fatigue building up during that 20-minute threshold run influenced their running mechanics. For the marathon, we just placed the sensors on the skin with some adhesive tape. For these measurements, we used a Lycra suit, which had pockets where the sensors were placed in. So that's easier for our calibration, easier for the measurement. It's a bit more stressful for the runner. The first measurements were in the middle of summer, where the runner had to wear a Lycra suit when it was in Celsius 35 degrees. I think that's about 95 degrees Fahrenheit, which wasn't very nice for the runners. We used the same 8 inertial sensor setup, and still had a cyclist next to the runner to receive data. Luckily for us, new developments allow on-body storage of the data, so we can get rid of the cyclist. Our aim was to identify parameters that change as a consequence of fatigue, and for the long term, eventually use these parameters during regular training runs to enhance running performance and prevent injuries. So this is our setup: a runner in a skin suit with 8 sensors, same locations as during the marathon. Cyclist next to it with a receiving part. This is our runner, and the previous running stick figure was more or less 2D. This one, you see the slightly bigger stride length, and it rotates, so it's completely 3D. So this is more or less the same stick figures you would get from your kinematic analysis in a laboratory situation with optical motion analysis system, but on the athletic track. So we defined some interesting variables from them: left and right hip angle, knee angle, ankle angle, tibial impact that we can measure easily with the sensor on the tibia. Center of mass oscillation and thoracal swing, so the movement of the trunk. This was our runner during the 20 minutes. Velocity, so he ran about 70 kilometers per hour, and his heart rate was, he ran about 70 kilometers per hour. Heart rate was about 180 at the end. But we defined 3 phases during the 20 minutes for which we collected the data. Basically, it was collected continuously, but we analyzed it only at 3 phases. We analyzed it only at the straight ends, so the turn might cause some, the turning in the track might cause some kinematic changes. And for this runner, we saw some interesting things for the knee angle at impact. For instance, for his right leg, there's a smaller knee angle at impact than his, for his right leg than is for his left leg. And his left angle has a different fatiguing profile than his right angle. For his left angle, a lot is happening during stance, while for his right angle, most of it's happening during swing. Peak tibial impact for his left leg has a different profile than for his right leg. So there are some differences between left and right. It can have a relation with the dominant leg, which we're not sure of that. Thoracal swing, we don't see that much, as well as for the septic muscle. There was a runner who ran 32 kilometers on a 10K, so it's a pretty fast runner. For 5 other runners, we developed the individual joint angle configuration. You see a lot of inter-individual differences. So this is the hip angle, which toe off about here. Knee angle, also toe off, and ankle angle, and here also toe off. So 5 runners from our selection of 10 runners, and we just plotted the average profile of their joint trajectory. You see enormous changes. For instance, if you look at peak knee flexion during swing, there's more than 50 degrees of difference between our the runner with the lowest angle and the highest angle. And they were all running on the same relative velocity, and their absolute velocity was also pretty close to each other. This is a picture that I took from the textbook of Perry, one of the classical works on motion analysis and gait analysis, a graph for running. So if this is our Usain Bolt and these are our Forrest Gumps, there's a lot of inter-individual difference compared to our, well, supposed to be normal knee angle. So this was also known before. What we did is we had our runners, they ran for 20 minutes on a 10K pace, and we identified the changes in their hip, knee, and ankle angle on the 3 stages for the right leg and the left leg. And we did a statistical analysis, repeated measures ANOVA, basically on every point of that trajectory of those different angles. And since we measured over 200 strides, you have for every point you have 3 data sets of 200 points which you compare. And if there was a significant positive increase, we gave it a green color. If it had a significant negative increase or decrease, it got a red color, and depending on the strength of the difference, it was more reddish or more green, even until blue. And what you see is that some runners have interesting changes. Runner 2, for instance, person 2, has positive increases on his hip angle on the right side, while negative changes on the left side. Same for knee, positive on the right, negative on the left. Other runners have exactly the opposite. Runner 5, for instance, a lot of negative changes. So negative doesn't mean not good, but in a different direction. So different changes in a different direction for his right leg and for his left leg. So we were missing one sensor for one runner. So runners change differently according to fatigue. So a very easy or very straightforward fatiguing protocol, 20 minutes running on an athletic track. This is for the hip angle, the same changes for the knee angle and for the ankle angle. And the maximum mean differences changed as well for the 5 runners. So some runners change more at the beginning for certain, for the left hip, for instance, that's over here. Others change more at the end. And there's a lot of inter and intra-individual difference in how runners fatigue. So still we don't know what exactly is a relation between fatigue and running mechanics, how you get fatigue, and how mechanics relate to that, but we see that runners fatigue in a different way and that their mechanics change intra and inter individually. 2 things that were pretty straightforward was the asymmetry. So we saw an increase in asymmetry during the course of that 20-minute run. We presented ACSM this year. So the as a consequence of fatigue, they were running more asymmetrical. Doesn't mean that they all got more asymmetrical. Some of them started asymmetric and got more symmetrical, but basically then there's an increase in asymmetry. And the other interesting factor was peak tibial acceleration. In 4 out of 5 runners, there was a significant increase in peak tibial acceleration, even during the 20-minute run on the athletic track. So 20-minute threshold run isn't that strenuous. For trained runners, it is fatiguing, but it's not exerting. Even then, there was a significant increase in peak tibial acceleration that could be witnessed. So, then we get to the take-home message. Runners are different, respond differently to fatigue. We don't exactly know how people fatigue and how that influences running kinetics. Probably because lab-based studies are not as specific as they can be, and there's an importance and a possibility of measuring those kinematic variables of running technique on the road. So Forrest can keep on running. And thanks to my co-workers. Thank you.
A few minutes for